Good morning and welcome to Information Retrieval. We begin a new module today. It's called Classification. As I indicated in the introductory notes, the form of classification that we're going to be doing is based on probability theory. There are other ways of doing classification. You could do classification with a decision tree. You could do classification with neural networks. But we're going to be talking about probability today, and probably probability. Let's spell it correctly right there. I'm going to assume that actually a lot of what I'm going to be talking about today here is review for all of you. But anyway, I want to assume that I have a fair die. For those of you that don't know what a die is, I get to draw it. It's this little wooden cube. There are dots on it. So that if I could draw the faces out individually, we would see a face that looks like that. We'd see a face that looks like that. 3 dots. 4 dots, 5 dots, and 6 dots. So that each one of these faces here corresponds to one of these. Again, we think about picking up this little cube and rolling it out, and what's going to happen is one of these faces is going to be facing up when we're done. The idea that it's a fair die, when we say that it's fair, it means that the probability of any one of these happening is the same. So basically that means that P of this is equal to P of this. And I'm not going to draw them all, but would be equal to P of this. Okay, the probabilities are all equal. And I guess what we're going to do is we're going to develop some of the rules of probability as we look at this particular example. We note that right over here, that this is my entire universe. In other words, my universe, we could call it U, is equal to this set right here, meaning that anytime I roll the die, I'm going to get one of these outcomes and no other outcomes. And the first theorem or axiom of probability is that the probability of the universe, which means that any one of these things is going to happen, is equal to 1. Okay? Otherwise, we know that if we have some event E that is actually a subset of the universe, then we know that the probability of E is someplace between 0 and 1. And in fact, over here, since we're assuming that it's a fair die, each one of these probabilities is the same, so that we get the probability of this is equal to 1/6, and the probability of this right over here is also equal to 1/6, and this goes all the way over to the probability of that right over there, and that's also equal to 1/6. This should be 1/6, not 6, because we note over here is that if we sum over E contained in the universe the probability of E sub I, that is going to equal 1, and the probability of 1, or if we add up 1/6 plus 1/6, and there are 6 of these, that's going to be equal to 1 as well. So we have a couple of other things here. So you might consider this an axiom. You might consider this an axiom. This over here is just a restatement of this one over here. So I'm going to call this 1 again. We have some other notation here. if I talk about if E is equal to the event that I roll a 1, then we can talk about E complement, and that's E complement, which is another way of saying not E. Well, if E is equal to this, then E complement is equal to the set that contains 2, 3, 4, 5, getting a little cramped here, 1, 2, 3, 4, 5, 6. So we can see that the probability of E complement is equal to 1 minus the probability of E, and in this case that would be equal to 5/6. So this is also an axiom of probability here. So let's see, I've got 1, 2, 3. And the axiom part is this part. Right over there. Again, I assume that this is all review. Okay, I want to consider another experiment. I've got a deck of cards here. So here's a deck of cards. And there are 52 cards. And I want to consider that I've shuffled these cards and I randomly pick a card. And I ask the question, what is the probability that it's the ace of hearts? If you can believe that that's a heart. And you would probably reason correctly as follows. You would say that there are 52 cards in here. Any one of them is likely if I pick a card at random, so that the probability of this is equal to 1 over 52. Okay? Now what I want to do is I want to ask you a question. I've got 52 cards and a fair die. And what I'm going to do is I'm going to pick a card and roll the die. And I ask you the question, what is the probability that I get an ace of hearts? I'm going to try and draw a heart. And I roll a 4. Now, when you think about this, you would realize that the probability of rolling a 4 has nothing to do with the probability of drawing the ace of hearts or vice versa. And in fact, what's going to happen here is that this is just equal to the probability of an ace of hearts times the probability of a 4. And in fact, that is going to be equal to 1 over 52 times 1 over 6. And we have to do some quick multiplication. That's 2, carry the 1. That's 1 over 312. Well, I think you all know where we're going with this. This is the notion of what's called independent events. Okay, and in probability, we will say that two events, A and B, if A and B are independent, then the probability of A and B happening is just equal to the probability of A times the probability of B. Now, I have a question for you. And maybe we'll leave this open for discussion and we'll see who chimes in with the answer. If the probability of A and B is equal to the probability of A times the probability of B, are A and B independent? And I will leave that for an open question. But now I have another question for you. We know the idea of what independence is, and I think that you would find it easy to believe that the act of drawing a card from a deck and rolling a die are going to be independent events. But suppose, again, I have a deck of cards, and I want to consider two experiments. In experiment 1, I pick a card, I note the value, I return it, shuffle, and draw a card. And I ask, for example, what is the probability of a 10 of diamonds followed by a 5 of hearts? And again, the thing to note here is that I picked a card, noted it, returned it to the deck, shuffled, and then drew a card again. These are, in fact, independent events. So that, in fact, this would be equal to 1 over 52 times 1 over 52. Now I want to consider a second example. I draw a card, note it, and I draw a second card. Okay? And now I say, what is the probability of a 10 of diamonds and a 5 of hearts? And here things are a little bit different, because when I come over here and I drew the 10 of diamonds, well, the probability of the 10 of diamonds is 1 over 52. But now I want you to notice over here that when I go for the second draw, there are only 51 cards left. Okay? So what has happened over here is this is now going to be times 1 over 51. Okay? Likewise, you might want to think about, suppose I would ask you the probability of a 10 of diamonds followed by a 10 of diamonds. Well, I hope you would believe that that would be 1 over 52 times 0 is equal to 0. If I'm going to draw a card, note it, and then draw a second card without putting that first card back in the deck, I can't do this experiment as an impossibility. Okay? So here is an example of where this second outcome over here actually does depend on what the first outcome is. And that brings us to the notion of what is called a conditional probability. And mathematically, a conditional probability, we write that this way. And what the way that we read that is as we say, what is the probability of A given that B has occurred? And that's a very different question. So for example, if I were to come over to you and say, what is the probability of drawing the 5 of hearts, given that we already drew the 10 of diamonds, you would say that that's equal, oh, well, that's 1 over 51. That is different than asking what's the probability of drawing the 5 of hearts. That would be 1 over 52. Okay? I hope intuitively this is all clear. Now, mathematically, it turns out that the probability of A given B, that's defined to be the probability of A intersection B over the probability of B. This is very important. Remember this, and we'll consider another example right now. Suppose I were to ask you the following. Again, I'm going to roll a fair die. And I were to say to you, what is the probability of rolling a 2? And you said it's a fair die, there's 6 possible outcomes, it's 1 over 6. But now I want to ask a different question. What is the probability of rolling a 2 given that I rolled an even number? So remember what this question is telling you. This question is, the fact that I'm telling you I rolled an even number means that I rolled either a 2, a 4, or a 6. And now what's going on is I'm saying to you, well, given that I rolled either a 2, a 4, or a 6, what's the probability that I rolled a 2? Well, I see 3 possible outcomes here, of which here's one of them, so it would seem to me that this is 1/3. Well, the probability of this given even, by our definition of conditional probability, is the probability of this intersection even over the probability of even. Well, what's the probability of even? Well, the probability of even, there are 6 possible outcomes, and here are the 3 even possibilities. So the probability of even, okay, is 1/2. And what is the probability of a 2 and even? Well, that's the probability of a 2. That over there is just 1/6. And this is equal to 1/3. So you can see that these two ideas agree.